Hello everyone, welcome to the presentation. This is Team 15 and our topic is synthesis of nanomaterials. Starting from approaches of synthesis of nanomaterials. The first one is bottom-up approach, where nanomaterials are produced by atom-atom assembly. And another one is top-down approach, where bulk materials are divided to produce nanostructured materials. The examples of each approach are given. Moving on to ball milling method. It is process of grinding material into a very fine powder using a cylindrical device filled with both the material to be processed and grinding medium. The principle is mechanical attrition. The rotation of container gives kinetic energy to balls, which in turn provide it to sample material, which helps in size reduction of the material. This is the process of ball milling. The key parameter is differential movements between the balls and collisions. These are process parameters of ball milling. First one is milling medium, which are balls. Example, lead balls, zirconia balls, silicon nitride balls, and tungsten carbide balls. Second one is milling speed. The video given explains the milling speed parameter. Then third, milling time. Then ball to powder ratio, which is vital for ball milling. And extent of filling of milling container is also a vital parameter. The advantages are given below. Less time is consumed, wider range of quantities, and low cost of production. The disadvantages are it has low working efficiency, produces loud noise and strong vibration, and relatively large electricity consumption, etc. Moving on to sol-gel method. The sol-gel process is a versatile and widely used chemical method for synthesizing nanomaterials. This process involves transitioning a solution into a solid through chemical reactions. Principle: the sol-gel process relies on hydrolysis and condensation reactions. These reactions create a three-dimensional network which forms a gel. Applications: production of nanoparticles, nanoporous materials, nanostructured films, quantum dots, and synthesis of zeolite. Moving on to the process. The process involves precursor selection, hydrolysis and condensation, salt formation, gelation, aging and drying, calcination and sintering. These are the reactions involved in sol gel process, mainly hydrolysis, condensation and gelation reaction. The key parameters are precursor concentration, pH control, temperature, catalyst. Advantages: precise size control, versatile structure, low temperature, homogeneous composition. Disadvantages: time consuming, limited to certain materials, contamination risk, complexity in scale up.
So let's move on to vapor deposition growth, commonly known as chemical vapor deposition. So this is a very popular bottom-up approach to deposit high purity and high performance thin films onto the substrates. Here usually the vapors of the gaseous substrate or a liquid is used so that it is transferred onto the material and condensed inside the chamber. So let's move on to the process. So as you can see, here is the main gas flow. It consists of the precursor gas that is used to transfer the main gas onto the substrate. So as the gas flow enters the chamber, here the gaseous phase reaction takes place and the gases are diffused onto the surface of the substrate where they react with the substrate and settle in over here, whereas the precursor gases that are used to transfer the gas are dissolved from the surface and are moved out through forced convection or vacuum pump. So you should make sure that the entire reaction chamber is free of any other gases, uh, since it would hinder the purity of the material, mostly oxygen depositing on the surface. So let's have a look at an animation depicting the same. So as you can see, these are the precursor gases. So as soon as the gas diffuses onto the substrate, there is a small layer of thin film forming over here, as you can see, and this is the gas outlet. Make sure the reaction chamber is heated at a particular temperature to maintain the substrates in a gaseous phase. So as you can see, the thin film keeps on growing. So let's move on to the next topic. Huh. Here we come with pulse laser deposition. So pulse laser deposition is a common process of physical vapor deposition where a high beam of pulse is hit onto a solid substrate that produces a cloud of ions which is later condensed onto the substrate. So main difference between physical and chemical vapor deposition is that in physical vapor deposition process, uh, a solid is used that is converted into an ion and deposited onto the substrate, whereas in chemical vapor deposition the material to be deposited is already in gaseous or liquid phase. So let's look at the process. So here is the reaction chamber, and here is the laser source that is moved on through a lens onto the target material that has to be deposited. So this produces a cloud of ions known as plume that is further condensed and deposited onto the substrate present over here, forming a thin film. So here is a vacuum pump that removes any other impurities present in the chamber, and here is a window to look at the same. So let's have a look at a video depicting the same. So as you can see, this is the reaction chamber. It should be a vacuum. Uh, so here is a lens. Here is a window that is focusing onto the target. So these are the target materials that has to be deposited onto the substrate. Here is the rotator that will rotate the materials one by one, so that when the laser hits onto the materials, forms a cloud containing all the ions. So here is the lens to focus the laser, and then here is the substrate. So here is a potential source to make sure the substrate is heated enough and the uh, target materials are deposited fine and even onto the substrate, leaving any gap. So vacuum pump to remove any air, and here is the pulse that keeps on hitting onto the substrate so that the ions move and deposit. So you can see the plasma plume forming over here. It consists of the ions of the target material, and here is the layer of thin film that deposits through this method. So I hope it's clear. So let's move on to the next topic. So applications of vapor deposition. So it is basically used in IC chips manufacturing, integrated circuits, and microelectronic devices, usually MEMS, microelectronic mechanical circuits, and NEMS, nanoelectronic mechanical circuits. So it is also used in the coating of anti-reflective mirrors used in most of the vehicles, and thin film solar cells, TFTs, etc. Then, whereas the pulse vapor deposition are usually used in the magnetic side to make thin magnetic coating onto the surfaces of many optical materials, and then it is very ideal for an even and wear resistant coating. So, thank you.
create 2D augmented IC circuits and other sensor circuits. Lithography is a process which is preceded by spin coating of a masking layer which then reacts. Lithography is a process of patterning on substrates, which is a top-down approach nanomaterial fabrication process used in the electronics industries. It is used to create IC circuits as well as other electronic circuitry such as sensor circuits. Lithography is preceded by spin coating of a masking layer which reacts to the medium of etching used in lithography, usually a photon beam or an electron beam. Lithography is then succeeded by a nanofilm deposition process like magnetron sputtering, which then sputters or deposits the metal onto the etched parts from the lithography. To understand lithography, we have a small animation. The substrate is first prepared by cleaning using acetone, and then a thin layer of photoresist is applied using spin coating. This spin coated material is then baked on a hot plate and later exposed to UV, and the exposed areas are then hardened or become insoluble or become more soluble in the first pre-wash solution. After the first pre-wash, these areas are then etched or removed apart due to it being more soluble in the developer solution. Then these parts are then exposed to magnetron sputtering and metal deposits onto the substrate only in these parts. After this successful deposition of the metal, the excess photoresist is then washed away using a final developer solution, which is a strong base, thus creating the pattern which is required onto the substrate. Lithography can be classified using two main classification features, which is medium of etching and type of mask used. On the basis of medium of etching, we can classify it as photolithography or E-beam lithography. Photolithography uses UV light, which is of the order of 20 to 100 nanometer, and the resolution size is up to 25 nanometers, all the way up to 5 microns. Electron beam lithography uses an electron beam created from a cathode ray tube, and the resolution is all the way down to 1 to 10 nanometers. On the basis of type of mask, we have masked lithography and maskless lithography. With masked lithography, a opaque sheet is used from which a shadow is produced when light is cast onto it, and this is then put onto a substrate. The resolution of masked lithography is less than maskless lithography. In maskless lithography, the beam of light or electrons are moved in 2D axis using mirrors in the case of light and magnets in the case of electrons. This beam is then used to create the patterns. As said earlier, magnetron sputtering is followed after lithography. Earlier, before magnetron sputtering, we were using thermal vaporization techniques, which vaporizes the metal atom which has to be coated. Following it, it requires extremely high temperatures to vaporize metals such as silver, copper, iron, etc. Magnetron sputtering, on the other hand, uses high voltage and is much easier to coat metals. The target is the metal required to be coated, and the substrate is patterned is the substrate that is received after patterning using lithography. Both of these are placed in a vacuum chamber, and the chamber is evacuated of oxygen so that the metal does not oxidize. Argon gas, which is a neutral and inert gas, is filled into the chamber, and a voltage of 2000 to 3000 volts is created between the anode and cathode. This ionizes argon to argon plus, and the magnets help in collimating the plasma beam between the cathode to the anode. The argon ions pass through the target, pick up few metal atoms, and then thus this is coated onto the substrate. To summarize, the steps to create a nanostructures for electronic devices include starting with spin coating of a photoresistive material onto the substrate, followed by electron beam or photon beam patterning onto the substrate, which is then pre-washed, and the exposed areas are then coated with a metal using magnetron sputtering, and then finally the excess photoresist is washed away in the last development stage. We have a lithography simulation which is interactive, can be downloaded and must be run with internet. Applications of lithography are various and wide. Primarily, they are used to create ICs for MEMS and NEMS. MEMS are microelectronic and mechanical devices. NEMS are nanoelectronic and mechanical devices. They can also be used to create optoelectronics such as LEDs, lasers and photodiodes. Various sensors such as photosensor, thermal sensor, humidity sensor are created using lithography. The new 5G and 6G antennas in mobile phones and other IoT devices are created on micron scale using photolithography. Processor and transistor arrays, which are these core of every single computer today, are also created using e-beam lithography. Other than this, magnetron sputtering can also be used to create highly reflective mirrors up to 99.99% reflective. Figure 2 shows an example of an aluminum mirror created by magnetron sputtering. Figure 1 is a photosensor which is created on silicon substrate using electron beam lithography.